Hello all, welcome to my course on methods of adhesion measurement theory and practice. We have already gone through lecture 1 and lecture 2. So, today we will have the lecture 3. It is a brief summary of what we went through in the last lecture. So, we actually used this well known divergence theorem to derive the stress equilibrium relations, and then we also showed that this stress tensor, which has got this 9 components, but 6 independent components. So, this is actually symmetric, and we also showed how to do the coordinate transformation. So, the stress component how can be transformed from one coordinate to the another. So, we have got x, y, z is one coordinate and x dash, y dash and z dash is the other component, and these are the direction cosines that we have, and we derived this stress components x dash is equal to like this and x dash y dash is equal to like that. So, like that we have got the several the other stress components we can also expressed by similar equations. So, today we will like to continue our this discussion, and we will like to first solve this example problem that from the last lecture. So, consider that we have this stress tensor 2, 4, 5, 4, 2, 4, 5, 4 and 0. The coordinate system let us say is rotated, so that the new coordinates x dash, y dash and the z dash have the following direction cosines here, direction cosines where x dash is represented, x is having this direction cosine x square root of 3 by 2 and with respect to y as half and 0 and like that. And so, therefore, we have this L1 is equal to square root of 3 by 2, M1 is equal to 1 by 2, N1 is equal to 0 and L2 is equal to minus half, M2 is equal to square root of 2 by 2, N2 is equal to 0 and L3 is equal to 0, M3 is equal to 0 and N3 is equal to 1. So, x dash is equal to xx plus ln square. So, xx is equal to 2 here and L1 square, that is root 3 by 2 square plus yy. So, the yy is equal to 2 here. So, this is 2 and m1 square. So, m1 is 1 by 2 square and plus this is zz. So, the zz is equal to 0. So, we do not have to worry about it, plus 2 xy. So, xy is equal to this 4, 2 into xy. So, here 2 into xy is equal to 4 into L1 and M1. So, L1 is equal to square root of root 3 by 2 and M1 is equal to half plus 2 yz. So, 2 y xy, y xy, yz and zx. So, yz, so yz is this component 4 into 4 plus 4 into M1 N1. So, M1 is half and N1 is equal to 0 plus this term will also be 0, because here again we have got the N1 and L1, N1 is equal to 0. So, it will be 0. So, we have actually here is equal to, so this is 2 into 3 by 4. So, it is 3 by 2 here plus we will have 1 by 4. So, it is 2 into 1 by 4 is half and plus we will have 2 into 4. So, it is 2 into root 3, something like this. So, we have here, so it is 2 plus 2 into root 3. So, it comes out to be about 5.464. So, like that we can also write down for x dash y dash L1 into L2 into xx. So, L1 is equal to root 3 by 2, L2 is equal to minus half into xx. So, xx is equal to 2 here. So, this is 2 plus m1 m2. So, m1 is equal to half and m2 is equal to root 2 by 2 and yy. So, yy is equal to 2 here. So, this is 2 plus this will be equal to 0, because n1 and n2 is equal to 0 here plus this particular term L2 m1 plus m2 L1. So, L2 is equal to minus half and L1 is equal to half here plus root 2 by 2. So, that is m2 root 2 by 2 into L1. So, this is m2 into L1. So, this is equal to L1 and this is equal to M2, write that into this is this term is equal to 4. So, that is yz. So, this is basically yz. So, yz is equal to this particular term 4. So, we combine all these terms. So, it will be root minus root 3 by 2 plus root 2 by 2 minus 1 by 4 and plus this particular root 6 by 4 here, root 6 by, it should be 2 by 2 into 4. I think I made a mistake here, maybe most probably into 4. Actually, we need to check this particular part. Maybe I think I should represent it by 2 into 2 root 3 by 4 here, it should be most probably. So, this particular term I will request the audience to check it, and then y dash is again can be represented like that. So, it will come out to be xx L2 square. So, L2 is minus half whole square plus M2 square is root 2 by 2 whole square, and here it is 2 into xy. So, xy is 4 here and L2 is minus half and into M2 is root 2 by 2 like that. So, again one can actually calculate it and one can get something like this. So, this is the way one can do this coordinate transformation using the direction cosines, and this stress tensor can be get transferred into something like this. So, today we will like to now discuss about the strain energy that gets stored in a body when it is deformed. So, application of surface and body forces on a body that deforms it, and as a result the energy gets stored in it, we all know. So, the slingshot case, that is a rubber film or rubber rod that gets stressed, and then the energy gets stored in it, and when it is relaxed this stone is thrown to a large distance. Similarly, this grasshopper this also stores its energy in its tissue and muscle, and then when relaxes it can jump for a very long time. So, we need to calculate this amount of energy that gets remain stored. So, this energy calculation can be done from the first law of thermodynamics, where we have this incremental work on the body plus incremental heat as applied to it, that should be equal to the increase in its kinetic energy plus increase in its intrinsic energy. So, that is the way it should be. So, we can actually this is the first law of thermodynamics, we can further derive it, we can obtain write this particular first law thermodynamics by this equation, where dW plus dQ. So, dW is the work done, incremental work done on the body, and dQ is the heat supplied to it, and delta K is the kinetic energy, and delta U is the intrinsic energy. So, over here this delta du, it has one component of this is basically the elastic energy inside the body. So, we can further derive this particular equation, and finally, we can get this elastic energy that remains stored per unit volume on the body because of its deformation by this particular equation, in which this capital XX, also these are the surface stress, those components of the surface stress that we discussed already is XX, and del EXX is the differential strain. So, differential normal strain, and this is del YY, it is differential normal strain in the y direction, then differential normal strain in z direction, and delta EXY, this is the differential shear strain, and capital XY, this is the stress that acts along the x axis on a plane that is perpendicular to the y axis, and like that. And so, we have this XXZ del EXX YY plus del YY then ZZZ del EZZ, and like that. And so, therefore, we can write this XX as this kind of partial derivative relations, del W by del XX with respect to the other components remaining constant. So, that will be equal to is capital XX, and like that we can write it like this. So, we can actually write here note of something like this. So, we need to have them to integrate this equation and this equation. So, we need to integrate this equation to obtain the elastic energy elastic energy in the whole body, and in order to do that elastic energy that integration, we need a relation between x and Exx. So, the stress and stress strain relation actually we want constitutive equation. So, the simplest constitutive equation that we can think of is known as the Hooke's law, and the Hooke's law generalized form states that every component of the stress tensor, so that is Xx, so that should be linearly dependent on every component of the strain component. So, the strain tensor. So, Exx, Eyy, Ez, Exy, Eyz and Ezx. So, so in essence what it says is that Xx is equal to C11 Exx plus C12 Eyy plus C13 Ezz plus C14 Eyz plus C15 Eyx rather Zx plus, okay, anyway does not matter, C1x Zx like that. So, this is the relation for the stress Xx component, how it is related to all the components of the strain. So, like that all the components of the stress can be represented linearly, and so as a result we can get this equation Xs is equal to C11 Exx and like that. And like that we can get for the Yy C21 Exx plus C22 Eyy plus C23 Ezz, C34 Eyz, C35 Ezx plus C66 Exy, and we can also get here Yz and Zx. So, these are the normal stress Stromal stress components, and these are the shear stress components. So, the shear stress components also is a function of all the strain components, and so therefore, we have C41 Exx plus C42 Eyy plus C43 Zz plus C44 Eyz, C45 Ezx plus C46 Exy. So, you can see, so there are 6 components of the stress, okay. These are functions of the 6 components of the strain. So, there are actually how many constants? So, 6 into 6 36. So, there are C11 to 666. So, there are actually 36 such coefficients or elastic constants of the substance. So, now it is not possible to work with all these 36 components and or having this so many constants. So, we can actually minimize the number of constants that is required to have this stress versus strain relations. So, for example, if you have an isotropic system, the formula connecting the stress components to the strain components remain independent of the directions. So, that means what it means is that what we have for the relation of Xx, okay, with respect to Exx, Eyy and Ezz, the similar relation should hold also for Yy and Zz. Okay. So, this relation should not change. What it means is that with respect to x, the y and z are equivalent. So, here for example, we have got Xx is equal to C1 like that. So, here this y and z for the x are equivalent. So, therefore, C12 should be equal to C13. Over here C14 Eyz is fine. Over here this Ezx and Exy. So, again there are z and y are there. So, which should be equivalent, and so therefore, this 15 and C15 and C16 should be equal. So, as a result, this equation should write it as C11 Exx plus here it is C12 and this is Eyy plus Ezz plus C14 Eyz and plus here these are equal. So, this is C15 let us say and Ezx plus Exy like that. So, this the equation, the relation should be like this. Now, if I write Yy, so again here it should be C11 Eyy, okay, plus C12 here instead of Eyy it will be Exx plus Ezz, for because y direction x and z are equivalent. So, therefore, here we should have Yy, we will have C11 Eyy and then C12 Exx plus Ezz plus C14. So, this is C14 and instead of Eyz of course, we will have Exz, okay, because with respect to y again z and z are equivalent, and so therefore, you have C15 and here it will be Ezy plus Exy like this, right. So, this is the way we can actually write for this Xx, Xx and Xyy, and then suppose that we have this Yz, this particular relation. So, over here again this for Yz x are equivalent, and so therefore, we should have here y z here, let us say y z equivalent here. So, here it should be C41 EXX, and this C42 and C43 that should be equal. Okay. So, this should be equal, C44 YZ is fine, and then this two term also C45 and this 46 that also should be equal. So, therefore, we should have C41 EXX plus C42 EYY plus EZZ, okay, because C42 and C43 that should be equal, okay, because y and z are equivalent with respect to x, okay, and so therefore, C42 into EYY plus EZ plus C44 EYZ, that is fine, and over here the coefficient for EZX and EXY that should be same, and therefore, C45 should be equal to C46, and we should have this. So, you can see that we have already reduced the number of coefficients, and like that we can use few other statements or few other conditions. For example, the stress strain relation should not alter when any of the two excesses are interchanged, or let us say any direction or direction of any axis is reversed. So, that means if I change from x to minus x, the direction of the relation should not change, and the stress strain relation remain unaltered also when the axes are rotated to a new position, that also should not change. So, when you combine all these terms, we can see this 36 coefficients that we had, that can reduce now to only 2. Okay. Only 2 coefficients are required to relate this stress versus and strain, that is what it seems, and these 2 coefficients or constants, these are represented here historically lambda and mu, and these are called the Lame's constants. So, these are basically the 2 relations which are required. So, therefore, the stress strain relations can be written as lambda into xx as a lambda into delta plus 2 mu Exx, and then this is the way that relation comes out to be after, okay, we apply all those conditions. From 36 now we have got the 2 constants. So, we have lambda into delta plus 2 mu Ex. What is delta? So, the delta is actually equal to Exx plus Eyy plus Ezz, that is delta. Okay. And so, the normal stress components we have lambda into delta plus 2 mu Exx, like that. Now, I can show you later on that this mu is called the shear strain and the lambda is shear modulus, and lambda is also related to this shear modulus, and there are few other kind of moduli I will just describe in a minute. So, here this Yz, so that is the shear stress, so that is equal to 2 mu is the shear strain into Eyz, here is the shear, mu is the shear modulus and Eyz is the shear strain. So, like that. So, the stresses are related to the strain, okay, by this kind of relations, and so Exx is what that we have defined earlier in the first lecture. So, it is del u by del x, and Eyy we have defined this as del v by del y, and Ezz as equal to del w by del z, and Exy we defined this as half of del u by del y plus del v by del x, and well, let us say Yz, so zy is equal to half of that is del v by del z plus del w by del y. So, x u v w are the displacements or deformation along the x, y and the z directions respectively. So, we have this, and the delta as I described is equal to Exx plus Eyy plus Ezz, and now we can substitute these relations into this stage the expression for the elastic energy per unit volume delta W, this is the infinitesimal quantity. So, for infinitesimal amount of increase in the strain, what is the infinitesimal energy that gets stored in the volume element per unit volume, that is this quantity. So, here we can integrate now. So, we have to integrate this equation to obtain the total strain energy stored, and it comes out to be equal to this particular expression. So, lambda by 2 into Exx plus Ey plus Ezz whole square plus mu into this particular quantity. We can also express this strain energy some other form, we will come to in a minute. So, now let us take a simple situation in which we have got an elastic rod here, okay, elastic block or rod whatever you say, and now let us say we apply is an uniaxial extension T. So, here the T is let us say this is the x direction. So, this T is actually equal to x x. So, there are no other forces applied in the y and z direction. So, therefore, this y y is equal to z z, this is equal to 0, right. And we don't have the shear strain also. So, let us say that x x is equal to T, and that is equal to lambda into delta plus 2 mu E x x plus 0, it is the y y. So, lambda into delta plus 2 mu E y y, and again z z is equal to 0 here. So, that is 0 here, is lambda into delta plus 2 mu E z z. Now, let us say we add up all these 3 equations. So, what we will get is T, that is equal to 3 into lambda into delta plus 2 mu, and this we will get here E x x plus E y y plus E z z, and I have shown it already that that is equal to delta. So, E x x plus E y y plus E z z, okay, that is equal to delta here, and so therefore, here this summation of these 3 terms will be equal to like this. So, therefore, this delta that we will get it as T over 3 lambda plus 2 mu like this. So, now let us say that I will write this expression, okay, into this. So, therefore, I will have here T, okay, is equal to lambda into T by 3 lambda plus 2 mu, okay, yeah, that is fine. It is equal to plus 2 mu E x x. So, this is we will get here, I created the left hand side over here, and so I will get here let us say 1 by 2 mu into 3 lambda plus 2 mu, and here I will get I will get here this is 3 lambda by minus lambda, so 2 lambda. So, it is 2 into lambda plus mu, I hope I am doing it right, and this is equal to E x x. So, here this 2 and 2 gets cancelled. So, you have lambda plus mu. So, yeah, so I have all done all this. So, we have actually lambda it here. So, E x x is equal to T into lambda plus mu by mu into 3 lambda plus 2 mu, and if I substitute similarly in this expression E y y equal to 0. So, 0 is equal to lambda into delta plus 2 mu E y y. So, if I substitute this expression over here and also say over here, okay, I will get an relation for the E y y and the E z z also like this. So, it will be minus lambda t by 2 mu by 3 lambda plus 2 mu. So, here we can see we have got something like this, that so we have got something like this here, E x x is equal to E x x is equal to this is T divided by mu into this is 3 lambda plus 2 mu divided by lambda plus mu. So, this quantity T, okay, T by this quantity, what is the denominator, is represented by E. So, E is known as the Young's modulus, and E is equal to mu into 3 lambda plus 2 mu by lambda plus mu. So, this is called the Young's modulus. You may have already heard of this particular term from your undergraduate days, modulus, modulus. Okay. So, this is called Young's modulus, and here this E y y divided by E x x is equal to E z z by E x x. What is this quantity? So, this is equal to actually minus of this, minus of E y y and minus of E z z. So, if I do that, then it will be it is lambda into t. So, lambda into t by 2 mu by 3 lambda plus 2 mu, and E x x is equal to 3 lambda. So, 3 lambda by 2 mu gets cancelled. So, let us get rid of. So, this gets cancelled and then we will have here t here. So, t also gets cancelled, t also gets cancelled, and we will have here 2 mu also gets cancelled. So, I will have lambda by lambda plus mu. I will have lambda by lambda plus mu. I hope I did not wrong. Correct. So, it will get lambda by 2 lambda plus mu. So, we will have a 2 here. Yeah, because of this 2 here, this 2 here, I will have 2 here, 2 here. So, lambda. So, this particular term, okay, this is represented by, let us say, sigma here, and this is called the Poisson ratio. This is called Poisson ratio. So, Poisson ratio defines that the strain that, so if you have a give a body uniaxial strain, so you have given body, so this is Exx, and because of the incompressibility or because of the this stretching in one direction, okay, this there is strain in the other direction, Eyy and also Ezz, in this direction. And so, the ratio of these strains in the Eyy by Exx or let us say Ezz by Exx, okay, that is given by what is known as this Poisson ratio, and Poisson ratio is represented by particular notation sigma, and in some cases is also represented by mu. Okay. So, in my lectures also might sometime by mistake I might represent mu also, but you should note that both sigma and mu both are actually same. So, sigma is equal to lambda by 2 into lambda plus mu. So, over here as it is, I have done it nicely over here. So, here as we already showed that this delta is equal to this particular term. So, that comes from the by after summation, if I find out the summation of these three relations, okay, it is simply comes out like that. And so, here as you remember this xx plus yy plus zz as we showed earlier in the earlier lecture. So, this is direction invariant, this is an invariant. So, it does not have any direction. So, this is represented by what is known as minus 3p, and the p is called the hydrostatic pressure. Hydrostatic pressure. So, if you remember in the fluid mechanics we use this particular term hydrostatic pressure to define the pressure of a fluid in a particular point, and this particular pressure does not have any direction, it is only magnitude. So, here too this has this xx plus yy plus zz, okay, this is you divided by 3 and negative sign, it becomes the hydrostatic pressure. So, as you know that as we have defined earlier, suppose you have the surface and the stress is away from the surface. So, let us say the x direction, so it is xx, okay. However, the pressure acts on this particular surface. So, this is actually p here. So, this is the pressure. So, the pressure and the stress is the opposite direction, opposite sign. So, therefore, this negative sign appears over here. So, here we take a delta is equal to minus p by we can write it here, delta is equal to minus 3p by 3 lambda plus 2 mu, and so that is equal to minus p by k. So, this particular term k is actually here, therefore, 3 lambda plus 2 mu by 3 here, it is represented by lambda plus 2 mu by 3. So, this particular quantity k is called the bulk modulus. Why bulk modulus? Because delta defines the xx plus yy plus zz, that is equal to volume strain. So, this defines that what is the change in volume with respect to the initial volume because of the forces that acts on this particular body, and so this is defined the volume strain. So, the volume strain is related to the bulk modulus and the pressure that is applied, hydrostatic pressure. So, minus p by k. So, k is known as the bulk modulus. So, here k is equal to lambda plus 2 mu by 3 and sigma. This is equal to this. Now, we can actually write down this sigma a little bit differently over here. So, sigma is equal to lambda plus by 2 into lambda plus mu, and here this E is equal to this we have already derived. So, we can write it like this, 2 sigma is equal to lambda by lambda plus mu, and so therefore, we can write it something like this, and so lambda is equal to 2 sigma by 1 minus 2 sigma into mu, and nu can also be written as E by 2 into 1 plus sigma, mu into 2 into 1 plus sigma, and so therefore, we have all these relations that the bulk modulus is equal to k is equal to E by 3 into 1 minus 2 sigma. E is the Young's modulus and mu is the shear modulus and k is the bulk modulus. So, you notice that when sigma goes to 0.5, this k goes to infinity. So, bulk modulus goes to infinity for an incompressible material which the volume cannot be changed. So, therefore, this particular material for which Poisson ratio is equal to 0.5, okay, this is basically the incompressible limit. So, incompressible material. So, we will take an example problem in the next class. So, thank you for today's lecture. Thank you.